Okay, so today we will show the projectile motion on the inclined plane. We know that there are three different types of projectile motion. One is the horizontal projectile motion, second one is the angular projectile motion, and the third one, which we are going to do today, is the projectile motion on the inclined plane. So, from the name itself, we can understand that this is the combination of the projectile motion and the motion on the inclined plane. So, by the inclined plane, we know that inclined plane, it looks like a right angle triangle, and the inclined plane makes an angle theta with the horizontal like this, right? And the projectile motion is like this. That means if we are throwing any stone or ball with an initial velocity u making an angle alpha, then we can say that the motion will look like a parabola. The path of the motion will be a parabola. So we are combining both of this one and this one. That means we are going to throw any kind of ball or the stone from the bottom of the inclined plane, and as a result the object will fall like this, and we are going to explain the entire motion which is happening on the inclined plane. So let's see how we can do that. Okay, so the motion in the projectile motion on the inclined plane can be two types. One is called the down to top. Down to top motion. What is that? It means that now at first we draw the inclined plane which is making an angle theta with the horizontal, and the down to top motion means that we are throwing any stone or ball from the bottom point of the inclined plane like this with the initial velocity u here. And let's consider that the initial velocity with which we are throwing the ball or the stone with the inclined plane is also making an angle alpha. What is alpha? Alpha is the angle made by the initial velocity u with the inclined plane, and theta is the angle of the inclined plane. Now, the second motion is the top to bottom motion. Top to down motion. What is that? Again we draw the inclined plane like this, and theta is the angle of the inclined plane which will be same. Now, instead of throwing the stone or ball from the bottom point, this time we are going to throw from upper position. Suppose here, here. So, and let us consider that the initial velocity with which the ball or stone is being thrown will be the alpha, this angle alpha. So these two are the two different types of the projectile motion on the inclined plane. One is the down to top motion, where we are throwing the object from the bottom point. Second one is the from the top to bottom, or the top to bottom. So at first we are going to discuss about the down to top projectile motion on the inclined plane. Okay, let's see. So Okay. Now for that, at first we need to draw the neat and clean picture of this entire phenomenon. That means at first we draw the inclined plane like this, and theta is the angle of the inclined plane. Now here goes the stone or ball, and initially we have thrown the stone with the velocity u vector, right? And this velocity u is making an angle alpha with the inclined plane. Okay. Now if we remember about the normal angular projectile motion, what is that? In the normal angular projectile motion, we used to throw the stone at the velocity u, which was making an angle, suppose alpha, with the horizontal direction, right? And there in the angular projectile motion, what we used to do, we split the velocity of the projectile, that is the u, into the two portion, into the x and the y component. X component of the u was the u cos theta, u cos alpha, which was along the x axis, right? And the perpendicular component or the y component was u sin alpha, right? So just like this, we have to apply the same logic in this case also. That means in the projectile motion on the inclined plane also. Let's see how we can do it. Now here in the projectile motion on the inclined plane, we use a small trick. What is that? Instead of considering the x-axis along the horizontal, we consider that the x-axis is along the inclined plane. That means along this direction here. That means y direction will definitely be the perpendicular to the x component. That means the y direction will be exactly perpendicular to the inclined plane. That means along this direction, right? Y direction will be along this direction, right? Okay, now let's do one thing. Just draw this picture slightly on the right side. Okay, so here this is the inclined plane, this is the projectile motion, this is the initial velocity u vector, right? And it is getting an angle alpha with the inclined plane. Now we have taken this direction as the x and this direction as the y direction, y axis, x axis, right? So just like the previous case in the angular projectile motion, we are going to split the initial velocity u along the x component and the y component also. How we are going to do it? Along this direction, we will say the component is the u cos alpha, right? U cos alpha along the x direction, and this direction is called the u sin alpha. U sin alpha. Okay, now here we have taken the x direction and the y direction. I mean the x direction is along the inclined plane. Now we can do it, because in mathematics we can rotate the x direction and the x axis and y axis by an angle theta. So here actually we are rotating the x axis by the angle theta with the horizontal, and all the other things will remain same. So let's see. So now we are going to draw another simplified picture of this entire phenomenon. How is that? x, y, this one. So here u, if this is the angle alpha, so u cos alpha, this is the u sin alpha. That means this is nothing but we are drawing the same thing here for the easier calculation, nothing else. Okay, let's see. So along the x-axis we got the u cos alpha, along the y-axis you get the u sin alpha. Now the most interesting part now comes. What is that? In the inclined plane, in the angular projectile motion, this one, in the angular projectile motion, just like the normal one, if you remember clearly that the u cos alpha term, that is the x component of the initial velocity, it remained constant throughout the motion as long as the stone or the projectile remains in the flight, right? But the y component of the velocity will gradually change. Initially up to the maximum height, it will decrease. Again from this point up to the last point, it will increase, right? That means the u cos alpha, the horizontal component of the initial velocity, remains same, because in this direction there is no acceleration, but in this direction the acceleration is the g. That's why the vertical component of the velocity will keep on changing, but the horizontal component of the velocity remain constant, right? But that's the case of the normal angular projectile motion. What happens in the inclined plane is totally a different case. How is that? Let's see. Okay, now see here. Okay. Now we know that if I draw any inclined plane here and the theta is the inclined plane angle, right? Theta is the angle of the inclined plane. Now look at this carefully. Suppose we have placed an object of mass m on the inclined plane, right? Now there will be now first we look at that which forces are being applied on this object. First of all, the weight of the object will be in the downward direction, that is the mg, right? Now if I draw a perpendicular from this one is the perpendicular, right? So this angle will be the theta. How it is theta? Simple. See, this is the right angle triangle, this angle is the 90 degree, this angle is the theta, so this angle is the 90 minus theta, and again this line is the perpendicular, this means this angle is 90, so ultimately this angle is the theta, right? So let's see. Okay, so if the mg is the downward direction, so this will be the mg cos theta. Simple, the component of the mg, and the horizontal component will be the mg sin theta, is not it? Because we are just taking the horizontal component and the vertical component of the mg. So the vertical component here will be the mg cos theta, but the horizontal component will be mg sin theta. Now see that here force is the mg cos theta, so this is the force is equal to ma, right? So mm cancel out, So acceleration in this direction is the g cos theta. Similarly, acceleration in this direction, that is the horizontal direction, is the g sin theta. Okay, now why we are doing all of this thing? Because the same thing is happening here also. That means here acceleration is in the downward direction, it is the g. Let's see now. Okay, so this is the g, right? This is the g. So just like the previous one, just as we have seen it, here this angle is the theta. So this will be the vertical component of the g cos theta, right? So along this direction, what we will get? We will get the g sin theta. Right? So g sin theta will be along this direction, and g cos theta will be along this direction. What are these? G cos theta is the vertical component of the acceleration being applied on the projectile, and g sin theta is the horizontal component of the acceleration being applied on the projectile. Now we can get all the ideas, all the components, and all the value of the quantity. Let's see. Now we'll write one by one what are those things. Okay, let's see. First of all, here, now look at this picture again. U cos alpha is acting along this direction, right? So U cos alpha is the x component of what? The initial velocity. So right, let's see. So x component of the initial velocity is the ux. What is that? U cos alpha. Y component of the initial velocity is the uy. So we write uy is equal to u sin alpha. Now look at that. Acceleration along the x-axis is the g sin theta. So we write ax. But see that here acceleration is in the downward direction, right? That means we have to write minus g sin theta, because g is always in the downward direction. So sine of the g will always be minus. So minus g sin theta is the x component of the acceleration. Similarly, y component of the acceleration is the, which one is this? This one, but minus sign also. So minus g cos theta. Okay, so we got the initial velocity x and y component, and also the acceleration value. Okay, g sin theta minus g sin theta is the x component of the acceleration, minus g cos theta is the y component of the acceleration. Okay, we got all of these things. Now finally we are ready to find out the three most important things. What are those things? Number one, to find out the time of flight. Number two is the maximum height. and number 3 is the range. Okay, let's see one by one how we can do it. Okay, first we start with the time of flight. Time of flight means the amount of time required for the projectile to remain in the air, right? So now let's see. For the time of flight, what we will do, time of flight. Okay, let's see what is that. So let's see. We'll consider the y direction motion. That means we will consider here only the motion in y direction. Motion in y direction. Okay. Now, in the y direction, what we have seen, that the uy is the u sin alpha, right? U sin alpha, and the acceleration ay is the minus g cos theta. That means minus g cos theta, and this one u sin alpha is the y component of the initial velocity. Okay, now let's see. Time of flight means the time required when the projectile moves from this direction to this point. Now see here, initial point is this one, right? And the final point is this one. Now if we consider the vertical along this direction, along the y-axis, what should be the net vertical displacement? Net vertical displacement, that should be 0, right? That should be 0, because both the initial point and the final point are on the same plane, right? Here, that means with respect to the y component of the vertical direction, no displacement is happening. So you can write Sy equal to 0. Now we will use this concept to find out the time of flight. Okay, let's see. Okay, so let's see the time of flight. Let time of flight is equal to capital T. So we use the formula S equal to ut plus half a square. So in place of the S, we are taking the Sy, right? Is equal to uy multiplied by capital T plus half ay capital T square, right? All the components of the y is here. Now see that Sy will be 0, as we have seen that net vertical displacement is 0. Uy is that u sin alpha, we just have seen it, this one, multiplied by capital T plus half multiplied by ay is the this one, but minus g cos theta. So minus g cos theta multiplied by t square, right? Okay, let's see now. So from this we can write u sin alpha multiplied by capital T is equal to half g cos theta multiplied by t square. Okay, let's see. One cancel out. So you can write from here the capital T is equal to 2u sine alpha divided by g cos theta. Let's see. So capital T is equal to sine 2u sine alpha by g cos theta. Okay, this is the time of flight. So first derivation we got. Let's see now. Now second one we are going to find out is the amount of the maximum height. Let's see how we can do it. Maximum height means, as we have known, from this point to here. This is the maximum height, right? So maximum height. Okay. Now that means the vertical net displacement will be the h max. Along the y direction, what is the displacement? Is the h max, maximum height, h max, right? And initial component, y component of the u is the u sine alpha. Okay, but the velocity at this point is 0, right? Now see, ay is equal to this one, that is the minus g cos theta, this one. So now we are going to use the formula v square equal to u square plus 2as. So let's see, we will just put the, okay, v is 0, u is here, actually the u sine alpha. So u sine alpha square plus 2 multiplied by, what is a? A is the minus g cos theta. So minus g cos theta multiplied by s, that is the h max. So from this we can write ultimately h max is equal to u square sine square alpha divided by 2g cos theta. Okay, so the second one is also done. Third one is the range. Okay, let draw the picture again. It becomes slightly messy. So this is the angle theta, and this is the projectile motion. This is the initial u velocity. This is the alpha. This is the y direction. This is the x direction. So along this direction we get the u cos alpha, and along this direction u sine alpha, right? So here along this direction is the g, along this direction is the theta angle, so it is the g cos theta, right? And along is the g sine theta. this direction, downward direction, right? Okay, now see, let's see here. Okay, so complete horizontal distance from this point up to this point along this is the called range. And here we have to consider the x direction of the motion, because range is the complete horizontal distance, so definitely we have to consider the initial x component of the u and a. So ux is the u cos alpha, that means the x component of the u, and the x acceleration along the x direction is that, which one, minus g theta, which is in the downward direction of the x component. So we write minus g sin theta here. Now the horizontal displacement is the sx from this to this is equal to r, and time required for the projectile to gain this horizontal displacement is the time of flight, because see, by the time the projectile will move from this point to this point, at the same time the projectile will have this complete total horizontal displacement, that is the time period, small t is the capital T. So again we use the formula s equal to ut plus half at square. Now here s is the what is, s is the range, right? So let's see, s is the range, we write r. Here u is the, this one, u cos alpha, u cos alpha multiplied by small t is the capital T, right, plus half multiplied by a is the, what is a is minus g sin theta, this one minus g sin theta, this minus g sin theta multiplied by capital T square. Okay, from this you can write, so we will put the value of the capital T. So u cos alpha multiplied by capital T is the 2u sin alpha by g cos theta minus half g sin theta multiplied by 2u sin theta by g cos theta whole square. So ultimately, after the long calculation, we finally get the value of the r, which is this. Two u square sin alpha divided by g cos square theta multiplied by cos of alpha plus theta. Okay, so this is it. In this way we can explain the entire projectile motion on the inclined plane.